In the last lecture, we have seen that a function of bounded variation can be expressed as the difference of two monotonically non-decreasing bounded functions on this interval AB. And in this lecture, we will see a differentiation theorem for functions of bounded variations and for monotone functions on compact intervals. So of course, boundedness for monotone functions is not required as an assumption for compact intervals, because a monotone function on a bounded interval will automatically be bounded if it is, whether it is monotonically non-decreasing or monotonically non-increasing. But now we can state the theorem that if f is a function of bounded variation on a compact interval, then f is differentiable almost everywhere. So here we have only assumed that it is bounded variation. What we will actually show is the following theorem, that if f is monotonically non-decreasing, then f is differentiable almost everywhere. So because a function of bounded variation can be written as a difference of two functions which are monotonically non-decreasing, then differentiability almost everywhere for both these functions will imply the differentiability of the function of bounded variation. So theorem, let's call this theorem 1 and let's call this theorem 2. So theorem 2 will imply theorem 1, and in fact we will somewhat weaken rather strengthen our hypothesis, and we will assume that this is a continuous function which is monotonically non-decreasing. So once we have established it for continuous function, then we will use what's called a continuous singular decomposition for monotonically non-decreasing functions, and prove it for both these parts of the decomposition. One part will be continuous and the other part will be a limit of what are called functions with jump discontinuity or jump functions. With they will also be differentiable almost everywhere. So let's look at the proof of theorem 2, which will imply theorem 1. So this theorem is going to have a rather long proof, and there are many lemmas that are needed for preparatory as a preparatory lemma, and we will do this step by step. So the first preparatory lemma that we need is that if you have a monotone function on a defined real valued monotone function on a compact interval, then it is measurable. So this is not very difficult to show, and I leave it as an exercise. The second preparatory lemma that we need is a very useful result called the Rising Sun Lemma, and it is due to Riesz, and it says that if f is a function from AB, a compact interval AB to R, so a real valued function which is continuous, then if you defined E to be the set of points in X, so this should be AB, set of points in AB such that there exists a strictly positive number h depending on x, so h is hx, such that fx plus h is strictly greater than f of x, meaning that the value that f takes at x is strictly lower than the value that f takes on a point which is strictly on the right of x. So then the claim says that this set E is an open set, first of all, and if E is non-empty, it can be written as a countable union of disjoint intervals a, k, b, k, k equal to 1 to infinity. So just a countable union of intervals of the form a, k, b, k, and E is a disjoint union of all these intervals. And the last part, which is the most crucial, is that for each k, either we have f a k equals f b k, or if one of the endpoints is actually equal to a, then f b k is greater than or equal to f a k. So before we proceed, let me give a graphical illustration why it's called the Rising Sun Lemma. So this is this picture we have here. So on the right hand side we have the rising sun rising from the east, so on the right hand side, and so that the rays of the sun are horizontally coming from right to left. So these are the rays of the sun, and if you have this function f in the green line, so this is the graph of the function f from a to b. So there will be points where the sun rays can hit directly on the graph of the function f. There will be some points where the sun rays will hit directly, and there will be some other points where sun rays cannot hit because they lie in the shadow area. So here these shaded points are the shaded area where the sun rays cannot hit, because you can think of them as mountains, and these are the so called valleys. And so here you can, so these are precisely the disjoint union, the intervals that make up this set E. So this is this interval, for example, from AK to BK, this is a subset of E, and here again this is a subset of E, except that when the starting point is itself the end point of one of these open intervals, then you no longer have AK equals BK. So if AK and BK lie in the interior of A and B, then f of AK will be equal to f of BK. So this is f takes the same value on AK and BK, except when AK is the starting point A, in which case FBK, so this is FBK, this is greater than or equal to FAK. Okay, so this is why it's called the Rising Sun Lemma. And now let's look at the proof of this lemma. So to start the proof of the Rising Sun Lemma, first note that since f is a continuous function, f is continuous, E is an open set. So I'll leave it as an exercise just by writing the definition of continuity and take a point x in E and produce an H positive such that in the interval x minus h to x plus h, so let me write this as IH, any y in IH also belongs to E, meaning that there will be, given this point y, there will be a point strictly to the right of y on which f takes a higher value. Okay, so this is not very hard to show, and I'll leave it to you as an exercise. And now we have an open set E, and any open set in R can be written let me take it in AB. AB can be written as a countable union of disjoint open intervals AK, BK or A, BK. So A can be included here or AK, B. So these can also occur in the disjoint unions, and in fact we will also consider these kinds of intervals in our decomposition of E into a countable union of disjoint intervals. So not just these kinds of intervals, but also where you can include A or include B, because these are also relatively open sets. So this set and this set, these are relatively open in AB. Okay, so this is a rather a general topological result that you can consult. For example, you can look at theorem 1.3 in Stein and Shakarchi book for a proof of this fact, that any open set in AB can be written as a countable union of disjoint open intervals, relatively open intervals in AB. So now we only have to show that for each k greater than or equal to 1, we have either FAK equals FBK if AK is not equal to A, and FBK is greater than or equal to FAK if AK equals A. So here in this case, the open interval that we consider is of the form A, BK, BK excluded. So this is the kind of so this is for the interval A, BK. So we let me just show this one, and I leave these this assertion also as an exercise, just by looking at the proof that we will see for the equality. When the equality holds, you can try to argue in a similar way to show that this inequality holds. So let's try to show that if AK equals FBK when AK is not equal to A. So to show this, first observe that neither AK nor BK belongs to E, because it's an open interval, so the endpoints are not included. So neither AK nor BK belongs to E, because these are interior points, and we are not considering intervals of the form A, BK or AK, B. Okay, so these are excluded. So in fact, I think you can also consider this one. It will be clear from the proof that we will give. So since for any x in E there exists an h greater than 0 such that fx plus h is greater than fx, and because AK does not belong to E, this implies that for all x greater than or equal to AK in AB, in AB, we have fx is less than or equal to fak, because otherwise if there was a point where fx was greater than fak strictly to the right of ak, then it would belong to E, and we have seen that ak is not in E. So in particular f of bk is less than or equal to f of ak. We now suppose that fbk is strictly less than fak, and we will arrive at a contradiction. We will show that this leads to a contradiction. Okay, so we have to show that fbk is equal to fak, so this will prove our result. So because f is continuous, by the intermediate value theorem, there exists a C which is between ak and bk, strictly lying between ak and bk, such that f of C is equal to f of ak plus f of bk over 2. So this is the average value of the values of the function f that it takes on ak and bk, and such a C exists by the intermediate value theorem. Now it could happen that there are many such points, infinitely many such points C. So what we will do is we will take the farthest to the right, the point C which satisfies this, we will take it to be farthest possible to the right hand side, so largest possible. So since the set f inverse fc is closed, this is a closed set, so the inverse image under a continuous function, this is going to be a closed set. We take C naught to be the supremum of points C in AK BK, such that f of C is equal to f of AK plus f of BK over 2. And this C naught is going to belong to the set, this is included in the set f inverse of fc, because it's a closed set. So in particular we also have f c naught is equal to fak plus fbk over 2. And now to arrive at a contradiction, we will show that there exists C prime strictly greater than C naught and C prime less than the right hand point bk. So bk here is the right hand point, such that f of C prime is also equal to f of C naught. This is equal to fak plus fbk over 2, and this is going to be a violation of the fact that C naught is the supremum of such values. So to show this, first note that since C naught belongs to E, there exists a point D greater than C naught, such that f of D is strictly greater than f of C naught. Now we also have that bk does not belong to E, so both these endpoints ak and bk did not belong to B. So for any x greater than or equal to bk, we have fx is less than or equal to f of bk, right? This implies that so we had f of d greater than f of c, but f of c is again strictly greater than f of bk because it's the average of the values of fak and fbk, and this implies that fd is greater than fbk, which means that d must be less than bk, because for all values greater than or equal to bk we must have fx less than or equal to fbk. So we have found a point between c and bk, strictly lying in the interior of these two points, such that fd is greater than fc is greater than fbk. So here we have f c, here we have f of bk, and here we have f of d. So the graph must go to fd and then come back to fbk. So by the intermediate value theorem there will be again another point c prime. So here I should take c naught rather than c. So this is c naught. So there is another point such that f c prime equals f c naught, right? So since fd is so I can just write similarly. So by the intermediate value theorem, the intermediate value theorem, there exists c prime greater than d and c prime less than bk, such that f of c prime equals f of c naught. But this is a contradiction. This is a contradiction which implies that f of ak must be equal to f of bk. So this proves the rising sun lemma, except that we still have to make sure that the inequality holds. So as an exercise, show that if ak is equal to the left end point a for the interval a bk, we have f bk is greater than or equal to f ak, which is fa. This should be almost immediate because f must be non-decreasing on this entire interval, because all of these points lie in E. So this whole thing is a subset of E. So f must be non-increasing. So I'll just leave it as an exercise for you to show. You can argue similarly, or you can give another argument to show this inequality. So this proves the rising sun lemma, and now we will use the rising sun lemma to establish our differentiation theorem for monotone continuous functions on AB.